There's one more operation when we talk about functions, and that's composition of functions. So we also want to try to define a derivative rule for that as well. So when we deal with chain rule, we're dealing with composition of functions, right? And we talked about f of g of x, but we're also used to seeing that as f of g of x. This one can get a little bit complicated because the notation is a little bit strange. But I'm going to try to make it as easy for you as possible. I'm going to show you the rule in general, though, regardless. So bear with me past this part. The derivative of the composition of f of g of x. We're going to work our way, actually I don't want to change it. We're going to work our way from the outside in. Right? We want to think almost about like stripping away layers every time. So from the outside in. So we're going to derive the outside piece alone. And we're going to leave it in terms of g of x. Well, we've already derived that piece, so now let's work our way in again. And I'm going to take that next piece and I'm going to derive the next piece. And I would keep working my way in until I can't do that anymore, right? So at this point, if I go any farther, my inside piece is just x. So there's really nothing for me to do there. So work your way in. If you notice, I didn't write this g of x in red because it's not really an operation I'm doing. I'm just writing f prime of whatever the thing is inside. I'm just looking at the thing inside. So even to look at a simpler example than the one that you kind of might see at the bottom of the screen right now. If I just look at something like, actually I'll basically do that example. 2x plus 1 squared. If I want to derive this, outside piece. Start with the outermost piece, and that outermost piece is just something squared. So the derivative of that something squared, right? Something squared turns into 2 times that something. So this is 2 times 2x plus 1. And then I take the derivative of whatever this inside piece is. The inside piece is 2x plus 1, and the derivative of 2x plus 1 is just 2. And then I can combine this, and I get 4 times 2x plus 1. And you can leave it that way. You don't have to distribute. Factored is fine. Let's take a look at essentially just the same exact example, just with a different power. So again, start with my outermost piece. My outermost piece is this cube, is something cubed. This outer piece is something cubed. And the derivative of something cubed, using the power rule, is 3 times something squared. Well, that something is going to be, it's not just x, because there's more than just x in the side, right? So my derivative is going to be 3 times whatever the something that we're dealing with is. So in this case, it's 2x plus 1 squared. Well, we didn't accommodate for that inside piece yet, so now we need to accommodate for the inside piece. Right, the inside piece is 2 times x plus 1. So the derivative of that is just 2. Power rule times 2. So I get 6 times 2x plus 1 squared. Chain rule. Right, take it small piece by small piece. This next one. You might be confused by the square root, but think about what we talked about before. We can always rewrite this using a power. This is 3x squared plus 2x to the 1/2. And now it's just a power rule problem. Use a little bit lighter colors here just so they show up a little bit better. So my outer piece is something to the 1/2. Something to the 1/2. And the derivative of that is just my power rule. 1/2 times the something to the negative 1/2. So let's start with that. G prime of x is 1/2 times the something. We're just going to basically ignore it for now. But now we need to account for it. So we've ignored it, now we're going to account for it. This is my something. right? This is that inside piece that I kind of just ignored for the time being. I get 6x plus 2. And I could leave it like this, but you might see it just simplified, and by simplified I just mean rewritten into a fraction. 2 times the square root of 3x squared plus 2x. You could even go farther and cancel the 2's out, and you have 3x plus 1 on the top with the 2 canceled out on the bottom. We're not going to worry about that right now. But that's your chain rule. Take it one layer at a time. Take it small piece by small piece each time. And you'll find that hopefully it's a little more manageable. So the next thing I want to talk about is what we call higher order derivatives. This is just taking further derivatives than just one derivative. Not as complicated as it might sound, right? So f prime we'll refer to as the first derivative. And of course, sometimes we write that as d by dx. Actually, let me move that up a little bit. Well, the second derivative we can write as f double prime, or d squared by dx squared. So it's the second derivative, right? F prime prime. It's the derivative of the derivative. Of the derivative. And then likewise the third derivative, f triple prime, or d cubed over dx cubed. Again, the derivative of the second derivative. Well, this prime notation gets kind of cumbersome, right? I don't want to go writing this because that's just ungodly. So we have this shorthand notation f to the n in parentheses, or d to the n over dx to the n, right? So if I want to talk about the sixth derivative, I could say f to the sixth of x, or d to the sixth over dx to the sixth. It just means take multiple derivatives. So f of x, here's one of my examples, actually from earlier in the videos for 4.3, and I want to find the second derivative. Well, there's no shortcut. We have to start by finding the first derivative. So we had done this one earlier in a video. It's just quick power rule. And the second derivative is the derivative of the first derivative. So I'm just going to do this again, 36x squared plus 4. And I could keep going if I wanted to. I could find the third and the fourth and the fifth. I could just keep on going, which is actually what we're going to do here. So the first derivative is 2. And the second derivative is 0. And well, I'm already stuck at a constant and 0. So any derivative I take past this point will still be 0, right? Derivative of any constant is still 0. So f to the fifth, we could say with some certainty, is going to be 0. In fact, any nth derivative is going to be 0 for, well, for any n greater than 1, right? So, you know, sometimes you see problems like this. You might see problems in higher or even higher orders. Try to spot a pattern. You don't sit there doing all the derivatives they ask for. Try to spot a pattern if you can. Sometimes one will come up.